Okay, let's talk about sex-linked traits now. Okay, so sex-linked traits, they're going to usually be on the X chromosome. This is because the X chromosome is just so much larger, and so it carries a lot more genes. And if there's a lot more, so there's a higher chance of having an issue because there's just so many more places to have an issue. And the Punnett squares are going to look a little bit different here. We're actually going to be crossing an XX female with an XY male. If it's an X-linked trait, which it usually will be, there's going to be a symbol on the X's, and you're not going to put a symbol on the Y unless it tells you it's a Y-linked trait. So most of the time, it's just going to be blank. So people like to use different notations for dominant and recessive in their sex chromosome. That should not say pedigrees. I'm going to fix that. This should say Punnett square. Sorry. Choose what works best for you. So some people like to use a little plus sign to show dominant and no symbol for recessive. Some like to do a big X for dominant and little x for recessive, which I wouldn't recommend just because it can get confusing if they like are kind of the same size since it's like the same exact symbol. So this third one is what I like to use. I like to say like a big A would be the dominant, and I put it on the X to show it's X-linked, and a little a shows recessive. Or some other system. So we're going to look at a picture in a second that uses another system. Just choose what works for you on the exam and stuff like that. Okay, so sex-linked traits. So there's a picture off to the side, and it just shows like the comparison of different things. So like everything in this top row right here is normal vision mother. Everything in the middle is carrier mother. Everything on the bottom is colorblind mother. And it crosses each of them with either a normal vision father or a colorblind father. Colorblindness is an X-linked recessive trait. So feel free to pause the video and kind of look through this and see where they get everything from, practice drawing it out. There's just a couple things I have this like picture here to take away. So, or a couple takeaways for it. Females can be carriers and being heterozygous, but males cannot. So notice right here, this is a female carrier because she has one recessive trait, and then so this way that these people did it that made the chart is that no symbol means dominant and a symbol means recessive. So she has normal vision because she has one dominant trait and it's masking the colorblind trait. But that can't happen in males because males only have one X, which means that if they get that colorblind X, they're done for, they're colorblind. Females could get one colorblind X and then be like, okay, but what's my other one going to be? And they might not be colorblind. So females need two of them in order to be colorblind. Males only need one. And then there's a couple of like little trends to notice. So for example, if you have a colorblind mother, every single one of her sons will be colorblind, but her daughters won't necessarily be colorblind as long as the father is not colorblind. And also notice the father only has one X to pass on. That's going to be important in a second. So pause if you want to and look through this chart. I like the chart personally, but if it's too overwhelming, that's okay. And we're going to move on and do an example together. So hemophilia is an X-linked recessive condition. A woman without hemophilia has a father with hemophilia. This woman mates with a man who does not have hemophilia. Draw the Punnett square for this scenario. So, a woman without hemophilia. So if she doesn't have hemophilia, that means that she can have two possible genotypes. She could be homozygous dominant, or she could be heterozygous. In both of these conditions, or both these genotypes, she would not have hemophilia. So the reason we're going to figure out, or the way we're going to find out which one she is based on some additional information. She has a father with hemophilia. What would that genotype look like? Well, we know it's male, so it's XY, and with hemophilia, it's X-linked recessive. Must be a little a. So keep in mind, the father only has one X to give, which means that if he has a daughter, he has to give that X away. So this X would go to every single one of his daughters. So that means that his daughter has to have an X little a. But we know she's not affected, which means that she has to have an X big A as well. So she must be heterozygous. So that's our woman, and she mates with a man who does not have hemophilia. This is a man, so he is XY. If he doesn't have hemophilia, that means he would have the dominant A. So that's our cross. We're going to go ahead and draw a Punnett square. Oops. Sorry. Okay. So I have my male on the top and my female on the side. It doesn't matter which way you put it. So in this box, we would have an unaffected female. In this box, an unaffected male. Right here, an unaffected female, but she's a carrier. And right here, an affected male. So that would be our little Punnett square. And then you could answer any questions based off of that. But that's generally how you would approach a problem like this. Okay. So the last thing I want to talk about with sex-linked traits really quick is the reciprocal cross. And it is important for you guys to recognize this term and know why it's important and why we use it. So basically, it's whenever you switch the male and female. So an affected female and unaffected male becomes unaffected female and affected male. So we just flipped who was affected and who was unaffected. And the reason this is important is to prove that a trait is sex-linked and not autosomal. So whenever you have an autosomal trait, switching the male and female results in the same exact F2 ratios. So imagine if you have in your parental generation, big A, and little a, little a. If I were to switch these, you end up with the same exact results. There's no differences. However, in X-linked, if you switch them, you end up with a different ratio. And so whenever you're trying to see, like, you find a gene and you're like, is it on the X chromosome or is it on one of the autosomal chromosomes? You can do a very easy test by just flipping the male and female characteristics and saying, okay, were the ratios the same as before? Are they different? If they're the same, it's autosomal. If they're different, then it's X-linked. So let's look at those different ratios really quick. Okay, so what I'm going to do is I'm going to have an unaffected female crossed with an affected male. So I'm not going to draw out the Punnett square for the F1 generation, but if you want to, feel free to do that on the side on a piece of scrap paper or whatever. But what you should end up with is that all females are carriers and all males are unaffected. And then I'm going to cross these two to get my F2 generation. And I am actually going to draw out this Punnett square just so you guys can see where everything comes from. Okay, so I have my female on top, male on the side. Again, it doesn't matter which one you put where. So here, unaffected female, unaffected female, unaffected male, affected male. So we have two unaffected females, one unaffected male, one affected male. Okay, now let's look at flipping these traits in the parental generation. So now I'm going to have an affected female and an unaffected male. Let's look at our F1. And again, I'm not going to draw out this pedigree, but feel free to on the side. We are again going to have heterozygote female carrier, and the males this time are all going to be affected. So notice there's already a difference here in our F1 generation. We had unaffected males and now we have affected males just by flipping the male and female. Now let's look at our F2 and see how those are different. Okay, so we would have an unaffected female, affected female, unaffected male, and affected male. So what are our ratios here? We have 1 unaffected female, 1 affected female, 1 unaffected male, and 1 affected male. Okay. So you'll notice the F1 and F2 generations are different. So what you need to take away from this is just why we use it, which is basically just to tell, is it X-linked or is it autosomal? Know that for X-linked traits, if you flip the male and female, you will get different results. And then know what reciprocal cross means. So if I tell you perform a reciprocal cross, you should know to flip the parental generations to be like just the opposite. So flipping the male and female traits. Yeah, so that's what I have over sex-linked. Let me know if you guys have any questions. Feel free to work through these problems on your own, draw out the reciprocal cross results, and all of that.
I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what genetics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are currently enrolled as a Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need to know about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online through Navigate, or just drop in during our open business hours. For more information about our current services, please visit our website. Thank you.